Hi, I decided to make this video to give you a brief introduction to Laplace transforms and how they'll connect to our study of differential equations. Of course, this material is available all over YouTube and the internet, but I know that you love the sound of my voice and you really want to hear what Dr. Hene has to say about Laplace transforms. A transform, so it's a fancy term, but all it means is it's a function or which we've seen before, an operator it's a function that makes functions. So the Laplace transform, which we're going to use this fancy L for, so it takes in a function of time. Usually we write it as like f of t, and it's going to produce a function of s. So it's a one-to-one map from one function to the next. And to be a transform, you need that to be reversible, right? So we're going to have the Laplace transform and the inverse Laplace transform. So that would be, if I start with my output, take me back to the input, f of t. So you can see this happens to be defined, the Laplace transform happens to be defined as the improper integral 0 to infinity e to the minus st f of t dt. So if you think about this, we're going to integrate with respect to t from 0 to infinity. So all the t's are going to disappear when we're conducting that integral. And what we get out will depend on the s parameter. So that gives us our big F of s. And that's just a convention to use t and s for the two variables. It doesn't exactly matter, but I'll try to stick to that just to lower the bar for how much you have to keep loaded in your brain when you're learning this. So for now, I'm just going to say that the inverse transform, which we denote with to the -1 there. So that's answering the question of what function. So it says, give me the function whose Laplace transform is big F of s. So the easiest way to think of these, at least initially, is when we compute any Laplace transform, we'll write it down and remember it, because if we read it backwards, we now know that the inverse Laplace transform of f of s is f of t. It's much easier to do calculationally to calculate the forward than it is the reverse here. So I think some simple examples here might help. So let's do the Laplace transform of the function 1. So this is, the function 1 is just a horizontal line, y equals 1, right? So we're saying, what does this function become after we transform it? This flat value of 1. All right, so f of t is 1, and all we're going to do is compute that improper integral. So I'm going to get -1 over s, e to the minus st. If you evaluate that, so you're going to take a limit, right? So the first term is going to go to 0, plus, so this is really minus 1 over s. So we get 1 over s. And so here's what I meant by the inverse transform. Now we know, once we've computed that, we know that the inverse transform of 1 over s is equal to 1. Okay, well, that's kind of strange. So that tells us that if I take a rectangle and I do its inverse transform, then I'm going to end up with 1 over s, right? So somehow a flat function becomes a asymptotic at 0. And then we can keep going, right? So for example, I did a calculation here off on the side for e to the minus st t, right? So now I'm doing f of t equals t. So let's figure out what the Laplace transform of t is. Well, so for this is an integration by parts, which is very common to have to do when calculating these. So one efficient way to organize that is what's called the tabular method. To do integration by parts, you do the derivatives and the integrals in columns. So this is the part that I'm going to take the integral of, so I'm just going to pass it down. And then you just alternate signs here and then multiply across. Right? So I'm going to keep taking derivatives till this term goes to 0. So if you do that and you evaluate it, you're going to get 1 over s squared. And we can start to pick up on a pattern here. So 1 gave me s squared, or t to the 1 gave me 1 over s squared. 1 by itself gave me 1 over s. And so the pattern is that t to the n gives me n factorial. So that's n times n minus 1 times dot 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 times 2 times 1 over s to the n plus 1. Great. So now I don't have to do this calculation every time anymore. I now know that if I'm given, say, the Laplace transform of t to the 4th, well, that will be 4 factorial over s to the 5th. That's an s there. So, which is what? So that's 24, 4 times 3 times 2 times 1, 24 over s to the 5th. And vice versa, right? So now, I now know if I see a 24 over s to the 5 and I do the inverse transform of this, I'll get back to t to the 4th. All right, so here's a key property of the Laplace transform, which enables us to not have to do a bazillion integrals when doing these. So if I have a function that's written as a times f of t plus b times g of t. So this is what we'd call a linear combination of the function f and g, right? So we kind of combine them up with a spice of an a spice of f and a b spice of g. Then, because the Laplace transform is defined as an integral, which is itself a linear operator, then this becomes a times Laplace of f plus b times Laplace of g. So we can split up them across a sum, and we can pull scalar multiples or number multiples out front. So here I just sort of worked this out. So this is the Laplace transform. This is just by definition here, which when we write it down as an integral, then you can, if you remember your integral rules, the integral of a sum is the sum of the integrals. So I can break this up into the two pieces, and I get, now using the definition of the Laplace transform, I get back to this. So let's think about how we can use this. So this Laplace transform of 2t squared plus t to the 4th, well, that is 2 times Laplace transform t squared plus 1 times Laplace transform t to the 4th, which we now know those from our table that we made up here. So this is 2 over 2 factorial t cubed, right? N factorial over s to the n plus 1. Oops. Switch my variable to s. S cubed plus, and then I actually just picked t to the 4th a second ago, so that's 4 factorial over s to the 5th. Boom, right? So in fact, because of this linear operator property, when we figured out t to the n, we actually figured out any polynomial. We can now easily, without having to do any integrals, we can find the Laplace transform of any polynomial. All right, and so then, in my day, we had to spend a lot of time looking things up in tables. So the whole idea is to avoid having to ever do integrals when you're doing these transforms. But these tables still exist, although they're better stored now in things like Wolfram Alpha or computer software that basically just look these things up in a big table that the computer has stored for you. But it's useful to have your own mini table that you develop for these, because having to type things in all the time can get quite annoying. So here, the Laplace transform of sine is 1 over s squared plus 1. The Laplace transform of cosine is s over s squared plus 1. And the Laplace transform of e to the t is 1 over s minus 1. So you could work those out by doing your integrals and doing integration by parts, and maybe that, if you want to practice your improper integrals, review those, then that's a good exercise. But for now, so that we don't get sidetracked too much into the details of computations, let's take those as given. And then, of course, I could work out now any polynomial plus sine, any polynomial plus cosine, or any polynomial plus exponential. All right, so now at the last little bit here, I just want to give you an introduction as to like why this is useful, right? Because it's not at all obvious why this weird, great, I invented something that takes in a function and produces another function and it's reversible. But that doesn't mean that it's useful, right? There's no Hane transform, right? So why does Laplace get to have his own transform? Well, it has to do with what happens when we take a derivative inside of a Laplace transform. So let's think about here, if I take the Laplace transform of df dt. All right, so, in Newton notation, I'm saying Laplace transform of f prime here. All right, well, we can plug that in, right? So we get e to the minus st df dt dt, right? So, and of course, you should hopefully have some memory that's jogged by seeing the integral of a derivative that makes you think of the fundamental theorem of calculus, right? Because the fundamental theorem of calculus tells us how derivatives and integrals are related. And when we have function times derivative of function, maybe you start thinking integration by parts. If not, then the further you go in math, the more you'll make that connection. So I can think of this as v times u prime dt, which I can replace using integration by parts as v times u minus v prime u dt, right? So integration by parts allows us to move the derivative from one term to the other. And we'll see why we want to do this in a second. So using the formula, right, 0 to infinity, e to the st f of t minus, so I'm just plugging in, right? So I've made this my v and this is my u, and u prime, and then I have to compute my v prime and my u from that to fill in. So we get our v times u minus v prime, so we get to move the derivative over, f of t dt, right, which is u. All right, so if we evaluate this, well, the first part's going to be 0 minus f evaluated at 0, right, because e to the 0 will be 1, minus, and then here, well, we can actually take that derivative. So that gives me a factor of s. Simplifying, I get f of 0 plus s, and then you might recognize that as just being the Laplace transform of f. I mean, that's just the definition that we wrote at the top of the notes. So this tells me that the Laplace transform of a derivative is the function evaluated at 0 plus s Laplace transform f of t. So somehow the derivative has disappeared in passing through this. All right, so this here is going to end up being some function of s times an extra factor of s, and this is that's a number, right? And in fact, you might recognize it in a differential equation, that's going to end up being an initial condition. So the Laplace transform allows us to convert a differential equation into an algebraic equation. So the derivatives disappear. So if we take that transform of it, then we can transform it, do some algebra, and then we'll have to transform it back to get back to our original system. So a quick example of this. So I think that we started the class with this ODE. Y prime is negative y. All right, so we already know that this is going to be an exponential decay differential equation. But let's see how we could solve this using the Laplace transform. So what you can do is I'm going to take the Laplace transform of both sides of the equation, and I'm going to start using the notation y hat is fancy L is the Laplace transform of y, just because this gets annoying for me to write at least. Feel free to maintain the fancy L if you want to, but this is the transformed version of y, if I put a hat on it. So I'm using our formula that we just found here, right? So this is the transform of the derivative is the value at 0 minus s times the Laplace transform function. And over here, this is just negative 1 times the Laplace transform of y. So let's group it together. So I'm going to put the factors of y over here, and I'm going to move my initial condition constant over there, divide through by 1 over s. So this is me doing the algebra, right? There's no derivatives left in this equation. And so cancel the negative sign, and we get y0 over s minus 1. And so at this point, we now have solved the equation for where the Laplace transform of our solution is equal to y0 over s minus 1. So you might see how we're going to use the inverse Laplace transform. Right? Because we have the Laplace transform of the solution to get the solution in what we call the time domains, put it back in the original coordinates, we need to invert that. So now we're looking for the inverse transform of y0 over s minus 1, which you might be able to figure out here from our table earlier that so the Laplace transform of e to the t is 1 over s minus 1. The Laplace transform of e to the minus t is 1 over 1 minus s. Oops, 1 over s minus 1. And so we get our Laplace transform back, and we get e to the minus t there, and we get y of t is y0 e to the minus t, which of course we knew that solution from numerous other techniques that we could use to solve this. So we'll see more about like why the Laplace transform is so useful. It's especially useful for systems, for our non-autonomous systems. And it comes up a lot in the engineering context. So hopefully before the semester ends, I'll be able to describe some of those contexts to you.